Mr. Tarou, in the next 3 math lessons, we are going to be taking a look at hyperbolic functions. Now, our calculus book says that they're only scratching the surface of this idea, this concept of hyperbolic functions, but yet, in scratching the surface, there's a whole lot crammed into this one section. So I'm going to break this up into 3 different lessons. In the first lesson, we are going to be introduced to, just what is the basic idea of a hyperbolic function, and be introduced to all the identities that go along with these functions. We can see some of them here, and I got some more on a green board. The next lesson we are going to be doing is looking at the derivatives and integrals of hyperbolic functions. We're not going to be doing that in this particular lesson. And then in our third video lesson, we're going to be taking a look at inverse hyperbolic functions. But in the first one that we're doing right now, what are we going to do after we look at the basic structure of a hyperbolic function? We're going to be evaluating hyperbolic functions given a particular value. One will require the use of a calculator, and one will require the use of our noggin, working with some natural log functions and natural exponential functions. And then we're going to go through 3 proofs. Now, I don't want to use the same problems that are in my textbook I'm making my YouTube videos, because that would probably run into some copyright issues. So instead of trying to make up my own proofs, which probably aren't going to work anyway, we're going to validate 3 of the identities you see at the beginning of this lesson to introduce you to how you might want to do those problems that are in your textbook. Okay, so let's get started. Hyperbolic functions are a special class of exponential functions that have a lot of similarities with trig functions. Yes, in the next 3 lessons, it's going to sound, a lot of what I talk about is going to sound similar to what you learned in trigonometry, but there'll be some small changes, so don't just try and remember the formulas and the rules and identities you knew back from trig. They'll be similar, not exactly the same. Trig functions are circular functions, and circles are a type of conic section, and conic sections, well, one particular type of conic section is the hyperbola. Now, that's all I really want to kind of say as far as maybe validating a little bit how hyperbolic functions are similar to trig functions. There's honestly a little, you might find a little more interesting comparison between the two in your textbook, probably in the first page of the section where they're comparing the area bound between the x-axis and a semicircle and a unit with a radius of 1. And the area bound between the upper half of a unit hyperbola and the x-axis. And they kind of give you a glimpse into how this idea of hyperbolic functions came about. As we go through our studies of calculus, you won't really see these come up that often. So whether or not, I'm saying maybe there's probably a pretty good chance your teacher is not going to require you to memorize the identities that are in this section, because you're not going to use them that often. But when you get into solving differential equations, well, the coarse differential equations, this concept will come back a lot more involved or integrated into your math work, your regular math work. Okay, so, but going back up here about them being a special class of exponential function, like trig, your hyperbolic sine and your hyperbolic cosine functions are going to build the other 4 basic trig functions. There are going to be 6, just like there was in trigonometry, or sine, cosine, secant, cosecant, tangent, and cotangent, only now I'll just say hyperbolic with them. And the sine, hyperbolic sine, and hyperbolic cosine are the sort of building blocks of the other 4, just like with basic trig. We have y is equal to 1/2 e to the x, and we have y is equal to negative 1/2 e to the negative x. These 2 exponential, natural exponential functions graphed here on the xy axis. Now, if you take those 2 functions and you add them together, again, this negative is already included on this bottom exponential function. If you add those together, taking the y values that you get from each of these functions, the most obvious being here in the middle, we have a y value of 1/2 and a y value of negative 1/2. Well, if you add 1/2 and negative 1/2, you get 0. So if you take the results of these 2 exponential functions and you add them together, you get this graph that honestly looks a lot like the trig function, the tangent function in trigonometry, basic trigonometry. But that is the graph of y is equal to hyperbolic sine of x, with a domain of, from negative infinity to positive infinity in a range which is the same. Now your graph of hyperbolic cosine, y is equal to hyperbolic cosine of x, is the result of adding y is equal to 1/2 e to the x, and y is equal to 1/2 e to the negative x. And taking those 2 exponential functions and graphing them and adding the results or the y values of each of those functions, we have this blue curve here, which is hyperbolic cosine of x again. And this is going to have a domain of all real numbers and a range from 1 to infinity. Now, your definitions or identities that go along with your hyperbolic functions, we have hyperbolic sine of x is e to the x minus e to the negative x over 2, and hyperbolic cosine of x is e to the x plus e to the negative x over 2. Hyperbolic cosecant is a reciprocal of hyperbolic sine, where x cannot be equal to 0 because you'd be dividing by 0, can't do that. Hyperbolic secant is a reciprocal of hyperbolic cosine. That all sounds the same as it did with trig. And hyperbolic tangent is hyperbolic sine over hyperbolic cosine, just like with basic trig. And we see here that hyperbolic cotangent is the reciprocal of hyperbolic tangent. So all that is looking very similar and really probably would not require any new memorization from what you already know, except for your graphs or identities for hyperbolic sine and cosine, hyperbolic cosine. Now, these hyperbolic identities, the first three look like the Pythagorean identities from trigonometry, but we know from those identities or rules that sine squared x plus cosine squared equals 1. Well, here we have a subtraction sign in the middle, so they're not exactly the same, they just look the same. And I don't really see any reason for me to read this off to you and keep saying hyperbolic this and hyperbolic that over and over again. Let me just show you these first three identities and break out my fancy picture-in-picture and give you the opportunity, get the glare out of the picture here, give you the opportunity to pause the video and take these notes there. We have some sum and differences here. We have some double angle identities going on here, and some what looks like half angle identities. Let's just pause, get these copied, and get through the 4 or 5 examples I said we were going to do in our lesson. I guess if I wanted to verbally say that correctly, relating it to what you learned in trigonometry, we'd think of these as our double angle identities. And I think I said double angle here, but I probably should have said half angle identities, because that angle is half of that one. But at any rate, let's get started on our examples. Our first two examples evaluate the function. What is the hyperbolic cosine of 4? Okay, this first one really is not going to be that exciting because we're going to need to use our calculator to come up with a decimal approximation of this answer. But remember, the hyperbolic cosine of x is e to the x, so e to the 4th, plus e to the negative x, or e to the negative 4th, over 2. Okay, well, obviously, again, we're not going to be able to evaluate e to the 4th or e to the negative 4th without the aid of a calculator. So right off the top of my head, that comes out to be approximately equal to 27.308. And okay, so that wasn't a very interesting first example. Let's get to our second one. What is the hyperbolic tangent of the natural log of 3? Okay, well, this hyperbolic sine and hyperbolic cosine is the building blocks of our other 4 trig functions. So, and I want to do this one without the aid of a calculator. So this is going to be equal to the hyperbolic sine of the natural log of 3 over the hyperbolic cosine of, again, the natural log of 3. And the hyperbolic cosine of x is e to the x plus e to the negative x over 2. And with this hyperbolic sine function, it's the same equation except with subtraction. So we're going to have e to the natural log of 3 minus e to the negative natural log of 3 over that common base of 2 is ultimately going to cancel with the numerator and denominator, but I want to show my work. So that's over 2. So that's your hyperbolic sine over hyperbolic cosine, which is e to the, in this case, natural log of 3 plus e to the negative natural log of 3 over 2. Okay, well, yes, we have one fraction over one fraction. So those, and a lot of times I show when you have a division of two fractions how we take that bottom fraction and flip it up, changing that division to multiplication, but we don't need to see that anymore. Now that we're in calculus, we're going to just allow these common denominators to cancel out, and continuing to clean this up, we know that the natural exponential function and the natural log function, those are inverse math operations, exponential functions and log functions. So these are also going to cancel out, and we get just 3 minus e to the negative natural log of 3 over, again here, 3 plus e to the negative natural log of 3. Now, of course, why didn't I cancel out this natural log in base e like I did over here? Well, you cannot do this. You can't cancel these inverse math operations unless the coefficient here is equal to 1. So we're going to bring these negative 1s up as exponent using the power rule for logarithms. And we're going to have 3 minus e to the natural log of 3 to the negative 1 power over 3 plus e to the raised to the natural log of, again, 3 to the negative 1 power. Just kind of pause and make sure I don't make any mistakes here, of course. Now our inverse math operations are going to cancel out. I probably should keep my color codings the same. And we're also going to write that 3 to the negative 1 power as 1/3. And we get 3 minus 1/3 over 3 plus 1/3. We need common denominators. That's going to become 9 over 3. And with those common denominators, we also are going to see this common denominator in the numerator and denominator of our big fraction cancel out as well, but we're going to have 8 over 3 over 10 over 3. Those denominators of 3 in the numerator and denominator cancel out. We have 8 over 10, which of course reduces to 4/5. And just let me check my answer before moving on. That is how you evaluate with, nothing exciting, just with a calculator and with our brains evaluating hyperbolic functions. Now let's move on to taking a given hyperbolic function's value, or using that value converted into the other 5 hyperbolic functions. No. Alrighty then, example 3. Use the value of the given hyperbolic function to find values of the other hyperbolic functions at x, and the given function is the sine of hyperbolic sine of x is equal to 1/3. Now, I like to do this with the trig functions being circular functions and all that nice right triangle trigonometry. I like to do these kind of problems in trig by having my kids set up a right triangle and not actually use the Pythagorean identities to convert that one trig function into the other 5, or help you find the other 5. But that is what we're going to do with these hyperbolic functions. So remembering here, let's see here. They almost look the same, but they're not. We have the hyperbolic cosine squared of x minus the hyperbolic sine squared of x is equal to 1. Got a minus sign there. So we are going to take this value of 1/3 that we're given for hyperbolic sine of x and plug it in here, and we get the cosine, hyperbolic cosine squared x minus 1/3 squared is equal to 1. And I'm using that first, I want to say Pythagorean identity, but that first hyperbolic identity, comparing, tying together the hyperbolic sine and cosine, hyperbolic cosine function together, because those are, again, the 2 building blocks for the other 4 trig functions. So once I find hyperbolic cosine, I can pretty much just write the other answers, which I'll do. I'll just step off and reveal those solutions one step at a time here in a second. So we have the hyperbolic cosine squared of x minus 1/9 is equal to 1. Add both sides by 1/9. And of course, making sure we have a common denominator, we have the hyperbolic cosine squared of x. 1 plus 1/9 is going to be 10/9. Square rooting both sides, we have the hyperbolic cosine of x is equal to the square root of 10 over 9. Of course, 9 is a perfect square, and we end up with the square root of 10 over 3. Now, with us knowing now what hyperbolic cosine is and what hyperbolic sine is, I'm going to go ahead and just step off and reveal the other 4 hyperbolic trig functions one step at a time. So you can pause the video and just try and write those out based on the identities, which are really, for those particular basic identities, the same as what you saw in trig. You just have to include that h. Or just watch the answers come up. Bam! Example 4. Proofs. Love them in trig. I'm sure we're going to love them in hyperbolic functions. With the hyperbolic functions, verify the identity. We're going to verify that the hyperbolic tangent of x squared plus the hyperbolic secant of x squared is equal to 1. Okay, well, just like we did in trigonometry when doing our trig proofs, we look, at our list of identities and see if any of these high power identities can help us match the left-hand side to the right-hand side of our identity. But since with our 3 examples we're going to be verifying a few of these identities, that probably is not going to be much help, and indeed, that is what I'm trying to prove right there. Okay, and there's no binomials to square, there's no common denominators that I can work through, there's nothing algebraically I can do to, obviously we're going to work with the left side of this identity first because it's the most complicated. There's nothing I can algebraically do. So, we're going to go into the building blocks of our hyperbolic functions like we did in trigonometry and work with hyperbolic sine and hyperbolic cosine. And our proof, now just for space purposes vertically, I really should write proof, and never mind, I'll just do that. Here's my proof. We're going to start with the left-hand side. And we're going to rewrite each of these trig expressions into their building blocks of hyperbolic sine and hyperbolic cosine. So we have hyperbolic tangent squared of x is equal to hyperbolic sine of x squared over hyperbolic cosine of x squared. Hyperbolic secant is 1 over hyperbolic cosine. Now this is nice. We're adding 2 fractions. That's something algebraically we can now do to try and get this to equal 1, and we already have common denominators. And if the right-hand side of my identity, or if my goal is to get this to equal 1, well, clearly a lot of stuff has to cancel out, and we don't want any functions at all left, whether they're basic trig or hyperbolic functions alike. So we need to figure out how are we going to get the numerator of this fraction to cancel out with the denominator. Well, there's a few ways to do that, and I'm going to kind of use the cheap way out for this first example and use one of these other identities, which is the cosine hyperbolic, so hard to say that, hyperbolic cosine of x squared minus hyperbolic sine of x squared is equal to 1. Well, my numerator is hyperbolic sine of x squared plus 1. And if I add on, now, when you're doing a proof, hopefully you know this from trig, you're not allowed to move things from, you're not supposed to really handle this like it's an equation. You pick one side of it and you manipulate it correctly, algebraically correctly, and with correct identities to make it match the other side. But you're allowed to move things around when you're trying to work with the identities and manipulate, these identities we're assuming to be true, basically, to prove a new identity. And if I add both sides by hyperbolic sine of x squared, I do get 1 plus hyperbolic sine squared is equal to cosine, hyperbolic cosine squared of x. So with that first identity I just pointed to here, this can come out, be replaced with, this numerator can come out and be replaced with hyperbolic cosine of x squared over hyperbolic cosine of x squared. And of course, when your numerators and denominators match, anything divided by itself, whether it's 5 over 5 or these hyperbolic functions, that does come out to be equal to 1. And we have made the left-hand side of this identity match the right, so my identity's done. Awesome. Now, awesome. But you might be going, okay, for lack of a better word, what to call it, because my textbook just gives you these, just says, here's your hyperbolic identities, and these look like those Pythagorean identities from just that core early trig class that we had. And you might be going, well, you sort of used one of those Pythagorean identities to take out your hyperbolic sine of x squared plus 1 and replace it with hyperbolic cosine squared x. And who's to say that that works? Who's to say, as our fifth example, that indeed the hyperbolic cosine of x squared minus the hyperbolic sine of x squared, who's to say that that actually is equal to 1? Well, now let's do a bit more of a fundamental proof here and work with the idea that these hyperbolic functions are a special type of exponential function. So for our fifth example, we're going to remember that the hyperbolic cosine of x was e to the x plus e to the negative x over 2, and that was squared, minus hyperbolic sine of x was e to the x minus e to the negative x over 2 squared. And, well, I'm worried about space. I probably should have, like I did over here, wrote, proof, and then started with the left-hand side as the beginning of my proof. So please forgive my little faux pas, my notation there. Now, we can see clearly that 2 squared is going to be 4, so that denominator is going to be easy to identify. Let's do some scratch work for the numerator. We have e to the x plus e to the negative x times e to the x plus e to the negative x, and distributing these two binomials together, we have e to the x times e to the x. Anytime you add like bases, you subtract, not dividing, let's try that again. Anytime you multiply like bases, you add those exponents. So we have e to the x plus x is 2x. We have e to the x times e to the negative x, and anytime again you multiply like bases, you add the exponents, and 1 plus negative 1 is 0, so we have plus e to the 0. Now don't be tempted to just say it's 0, because we're talking about the exponent being 0. And anything to the 0 power is equal to 1, not 0. Again, we have e to the negative x times e to the x is another e to the 0 power. And then e to the negative x times e to the negative x. Well, negative 1 plus negative 1 is negative 2. So we have e to the 2x. We have 1 plus 1 is equal to 2. And then we have plus e to the negative 2x over 4. Now minus, and I'm going to make sure to keep this right-hand side wrapped up in a set of parentheses because I want to make sure to distribute that negative through all of the terms that's going to be in my numerator. And if you want to see the arithmetic, obviously we're just looking at a sign change, so I can include a couple of negatives in there. We're still going to have e to the 2x. Then we're going to have minus e to the 0, and another minus e to the 0. And then still, though, negative times negative is positive. So over here we have e to the 2x power. This is 1. This is 1, so negative 1 and negative 1 is negative 2. And then e plus e to the negative 2x. And I don't think by this point in calculus I need to rewrite that distributing the negative sign. So we have a common denominator of 4. We have e to the 2x minus e to the 2x, which is going to cancel out. We have positive 2 minus a negative 2, which is 2 plus 2, which is 4. And hopefully that's all the bigger I need to make that fraction bar. e to the negative 2x minus e to the negative 2x. Those are going to cancel out as well. And we have 4 over 4 is equal to 1. So indeed, I have proven that the hyperbolic cosine of x squared minus the hyperbolic sine of x squared is equal to 1. That means that back here in this other, my first proof, that substitution was valid. And, you know, I've got 2 good proofs here and just 1 more left to go. Bam! And for our last example, we're going to prove this half-angle identity right here, that the hyperbolic sine of x squared is equal to 1 minus, let's try that again, negative 1 plus hyperbolic cosine of 2x over 2. See, that angle is twice as big as that angle, or that angle is really half as big as that one. Okay, at any rate, what we're going to do with this is I'm going to start off the first couple of lines and then reveal the rest of the proof one step at a time, because it's going to look very similar to the algebra and that work with that natural exponential function we just got doing in our last example. Okay, so the hyperbolic, we're going to start with the right. And the proof is, starting with negative 1 plus, clearly the most complicated portion of this identity, negative 1 plus the hyperbolic cosine of 2x over 2. No basic algebra to work on and finding common denominators or squaring binomials. There's just nothing there. So we're going to go to those core, those building block type identities, and that is the fact that the hyperbolic cosine function is a special type of exponential function, going way back to the beginning of our lesson, showing you how the hyperbolic cosine of, you know, something, in this case, the angle of 2x, or the value of, the angle of 2x, we have negative 1, or the value of 2x, plus, now, hyperbolic cosine again was, hyperbolic cosine of x was e to the x plus e to the negative x over 2. Well, now that something, or what I was saying, x in here is 2x, so just write 2x instead of x. So we have plus e to the 2x plus e to the negative 2x over 2 all over our denominator of 2. And now, you know, can we manipulate what's going on here to match the idea of it being equal to hyperbolic sine of x squared? Now I'm going to reveal part of this proof, or most of the proof, right up near the end, one step at a time. So you might want to pause the video and try this on your own before you see the rest of the solution. Okay, so I fibbed a little bit. I didn't reveal the entire proof, but I got to a point where I think a lot of my students, especially when you're back and you're first learning trig proofs, that some students would get stuck here and not exactly know how to turn this expression into something that eventually becomes hyperbolic sine of x squared. Now, you know, we are in calculus now, not trigonometry, so maybe this is over-explaining this a bit, but in case you do struggle a little bit with trig proofs, and I do struggle with general proofs, or just proofs in general, but I do love me some trig proofs. And what I would think is a very good idea at this point, if you start here and you go, well, okay, I see some exponents of 2x here, where ultimately my function, or my value, excuse me, going into the hyperbolic sine function is just simply x, not 2x. How do you bring that down? Well, when you're doing proofs, don't forget the answer is staring right at you, and let that answer guide you if you get stuck through the journey of this proof. So if you want to do some scratch work on the side here for a second and understand that this has to become, well, if this identity is true anyway, hyperbolic sine of x squared. Well, let's do some scratch work and kind of go in reverse and see if we can't meet in the middle somewhere. Hyperbolic sine of x. Well, that's e to the x minus e to the negative x over 2, and that's squared. And we just did this on the previous problem, so I'm going to just run through this a little bit quicker now. E to the x minus e to the negative x squared this times itself is going to be e to the x times e to the x is e to the 2x. We have a negative here, so we're going to be doing a positive times a negative, so that's going to be minus e to the x times negative e to the negative x is going to be negative e to the 0, and that's 1, and there's 2 of those. So we're looking at minus 2, and then finally plus e to the negative 2x over 2 squared is 4. That's where we are right now on the proof. So actually we're just a couple of steps away from finishing this proof, and with this scratch work, really I'm just going to copy these steps in reverse. So this, I guess you can kind of argue, is sort of like that perfect square trinomial that we took a look at in algebra and algebra 2. Probably haven't said that in quite a while. And so this becomes e to the x, because we can see the scratch work there, minus e to the negative x over 4, well, no, it's 4 here and there, over 2 squared, and e to the x minus e to the negative x over 2, that's your hyperbolic sine of x. So we have hyperbolic sine of x squared, and that is the end of our last example, and that is the end of this first of 3 lessons about hyperbolic functions. I'm Mr. True. Bam! Go do your homework. Or better yet, watch parts 2 and 3, which I'll have links to in the description of this lesson. They'll be in there as soon as they're done.